In the standard enterprise model for managing remote IoT devices, telemetry and media route into a massive, centralized hub like AWS or Google Cloud. Routing sensitive data through third-party servers creates a permanent privacy vulnerability. Tracking proprietary fleet movements or capturing secure audio and video requires handing that raw intelligence to a provider you do not control. This architecture also carries a compounding financial penalty. Commercial clouds charge by the byte for bandwidth and storage, meaning a fleet of hundreds of devices generates rapidly escalating monthly costs. Achieving high-performance tracking and media ingestion without these trade-offs requires a self-hosted edge architecture, bringing the server physically under your own roof. This sovereign architecture runs on a single Raspberry Pi. This credit card-sized computer handles the processing and storage tasks usually reserved for server racks. Scaling a secure tracking system without sacrificing privacy requires abandoning the commercial cloud and rebuilding the network architecture from the edge inward. A location tracker must simultaneously manage two conflicting data profiles: real-time GPS coordinates and heavy remote media files like photos and video. Managing these on micro-hardware requires a bifurcated network architecture, which splits the traffic into two distinct pathways based on the data's function. This separates asynchronous command signaling, the brief text-based instructions telling a device what to do, from the synchronous high-bandwidth streaming of heavy payloads. Routing a massive video file through the same protocol used for a tiny GPS ping creates a bottleneck that chokes the micro-hardware. Scaling a micro-hardware node to manage a fleet requires this strict division of labor, routing data based entirely on the weight of the packet. The system begins with an Android client node in the field and the Raspberry Pi server in your facility. The auto-registration system generates a unique digital ID token the moment the app opens. This token maintains a persistent, authenticated state, so the connection remains active even as the device moves between cellular towers. To communicate with that token, we use Firebase Cloud Messaging, or FCM. FCM is a cross-platform messaging solution that allows us to deliver instructions across different network conditions. We use FCM strictly as a signaling layer. The dashboard sends a low-weight instruction, like send GPS, through FCM to the phone. The resulting heavy data never travels on this path. Since these signaling packets are strictly text-based, the system inherits the scale of Google's FCM infrastructure, which manages millions of concurrent devices. Once the phone receives the signal, it sends the physical GPS coordinates back to the Raspberry Pi for local ingestion. These incoming pings are written to a local SQLite database. SQLite is a lightweight, self-contained database engine capable of processing coordinates from over 100 concurrent devices simultaneously on a single Pi. Offloading the command routing to FCM allows the edge hardware to focus its entire computational budget on processing and storing the incoming telemetry. While GPS pings are lightweight, the system also features remote media control to trigger photos or audio recordings. When these heavy media files are captured, they bypass the FCM signaling layer entirely. These media blocks are pushed directly from the phone to the Raspberry Pi storage. This direct ingestion ensures the data never touches a corporate cloud server. The server organizes this data using a hierarchical local storage system. Every file is sorted by device name, the date, and the media type. The total capacity for this media is limited only by the physical hardware attached to the Pi, such as a microSD card or an external hard drive. A standard 128 GB drive can secure tens of thousands of media files locally. This direct-to-disk architecture achieves absolute data sovereignty, keeping all sensitive media files within your own physical hardware. The high-quality Live View feature is the most resource-intensive component of the tracker. It uses MJPEG streaming, or Motion JPEG, which delivers a continuous stream of individual image frames to the operator's browser. The Raspberry Pi must process this feed in real time, rotating every frame 90 degrees to correct the viewing angle. A GPS ping is an intermittent blip of data. In contrast, an MJPEG stream is an unbroken fire hose that forces the processor to work continuously, increasing the thermal load on the chip. This continuous demand creates a strict empirical limit. A Raspberry Pi 4 or 5 typically caps out at 3 to 5 concurrent live streams. Exceeding this threshold causes network latency to spike and frame rates to drop as the processor reaches its computational limit. Stability at the edge depends on disciplined resource allocation. Respecting the physical hardware limits of live streaming preserves the performance of the GPS telemetry and media storage systems. Beyond the hardware limits, managing a large fleet requires a system for human operators. Scaling to multiple operators requires a multi-tenant architecture to isolate different user groups. We use role-based access control, or RBAC. This is a method of restricting system access to authorized users based on their roles. In this model, an admin assigns specific device clusters to individual managers. User device mapping allows the admin to strictly partition visibility. This ensures that a manager can only see and control the specific devices assigned to their account. Logical partitioning transforms a single edge server into a professional, multi-operator fleet management system. The all-in-one dashboard brings these layers together. Telemetry, media organization, and live streaming are unified in a single UI. The system maintains low latency by routing instruction signals through FCM while keeping heavy media payloads on a direct path to the local disk. This closed-loop edge architecture provides security benefits that commercial cloud hosting cannot match. This solitary microcomputer board provides high-level fleet management capabilities at a fraction of the cost of traditional infrastructure. The system operates on one central architectural rule: always match the protocol to the weight of the data. Absolute privacy and fleet-wide scalability are achievable through disciplined systems engineering at the edge, independent of enterprise cloud budgets.